Hi guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all our members to my channel and also request us to subscribe, ring that notification bell to be getting other updates on our various uploads we do in mathematics and sciences, and also of course check our description boxes for various links of other similar videos which we are going to do in topics in mathematics and sciences. Now, in our discussion today, I'm going to look at a result of experiments which were done. And this, of course, are going to summarize some of the laws which we are going to come across, especially on electromagnetic induction. Now, these are going to be works credited to two specific, of course, individuals whom we're going to look at in this particular case. And these are the works of Michael Faraday and, of course, this Russian scientist by the name Lenz. In this case, then, therefore, we are going to look at this specific, of course, laws which are going to culminate into electromagnetic induction and, of course, other laws which are going to assist us in trying to interpret the experimental results which, of course, have been obtained in this particular case. Now, I've given two particular illustrations, perhaps, which I can give in terms of A and B. And these are going to assist us in trying to, of course, interpret the phenomena which, of course, we had mentioned in our previous video on the concept of electromagnetic induction. But specifically for this case, it's going to assist us in trying to determine the direction and the flow of current, and what are some of the factors which are going to affect the magnitude of this specific current. Now, in this case, suppose I have a bar magnet shown as such. We can consider this bar magnet taking note of these polarities for north and south. We had said that these magnetic field lines are going to run in this specific direction shown as that. And there are some basic rules which we had, of course, quoted for these magnetic field lines, which, of course, we can just look at this on as symmetry and other factors which we are going to consider. But in this case, I'm going to use this simple illustration, whereby we're going to have this specific magnetic field lines given as such. And then we're going to have that one shown as such. So if this specific magnet is brought near a coil, so perhaps I can give this one in terms of a coil shown as such. So just going to have a rough sketch of a coil. So this is a coil that's made up of a number of turns, which we are going to consider in this case in our specific experiment. So if this particular coil is moved in a relative motion relative to this specific magnet, we're going to see that the coil is going to be cutting some of the magnetic field lines which are going to be shown above, and this is going to be resulting in the induction or the induced current which is going to run inside the coil. And this current is going to be running in this particular direction, as we're going to see later. So in this case, from the first experiment, which we of course, the first illustration which I've given for P, we're going to consider the motion, whereby we're going to consider the motion of a relative motion of this specific coil relative to this specific magnet. In case whereby we're going to have a forward motion and, of course, the reverse motion, and try to see what are some of the effects on this specific direction of the current, which we're going to, of course, be realizing from this particular case. Now, I'm going to consider this particular experiment, and in this case, we're going to see that if this specific, of course, motion of this specific magnet is going to be moved in this particular direction relative to the coil, we're going to see that this specific coil is going to be some current is going to be induced to the cutting of these magnetic field lines which I've mentioned, and the specific current is going to be flowing in this particular direction which I've shown using the arrows. Now we can identify this particular direction of the motion of this specific current, or the direction of the current, by using this particular notation from the Lenz law, which we are going to see later. Now I mentioned the works of Lenz. Now the Lenz law is going to be handy in order or in assisting us trying to define the direction of this specific current. And the Lenz law, of course, is going to play a vital role in trying to particularly identify this current, which I've said, which is going to flow in these two specific, these two specific loops, try to identify the direction as I've said. And this law states that the direction of an induced current is such as to oppose the change causing it, whereby, perhaps I can, direction of induced in summary form, current is such as to oppose of course, the change causing it. The space is small, but I hope that it's going to be comprehensive. So this is going to be relying, the direction of the flow of this specific current is going to be relying on Lenz's law. And this law states that the direction of the induced current is such as to oppose the change causing it. Now, the specific wording of this specific term from the Lenz's law is what we are going to consider. Now, from our previous discussion on the laws of attraction and, of course, repulsion for magnets, we said that like poles are going to, of course, repel, and unlike poles are going to attract in this specific case. So if we try to consider in this particular case, if we are moving this north pole of the magnet in this particular direction, from our Lenz's law, we are going to expect a specific scenario whereby the effect which is created is going to oppose this specific motion. And this, from the laws of attraction, is going to be a like pole, which is going to be magnetic node. So in this case, from this particular coil, if we try to look at it from that specific direction, we can look at it from this particular notation of a north pole which is opposing another north pole which is coming in. Now, the motion of this specific magnet then therefore is going to create an effect which is going to be a repulsive one, which is opposing the change causing it. Now, if we consider the second case, we're going to have this specific magnet being withdrawn from the coil. And if it's withdrawing from the coil, then therefore there's going to be an attractive effect which is going to cause opposition to this relative motion which is going to be caused away from the coil. Now, this is going to be creating, if we try to look at this specific coil from this direction, and therefore it's going to be creating a south pole, which we can use this specific notation in trying to identify it. Now, the effect of this, as I had mentioned from our previous discussion, is that there's going to be a deflection of the coil. Now, the motion towards the coil is going to cause a deflection towards the right, relative to this specific, of course, experiment. And of course, the second one is going to be a motion away from the coil is going to cause a deflection in the opposite direction. And this, of course, is going to be relying on the two basic laws which we have mentioned, particularly the Lenz's law, and we're going to look at the other one, which is basically going to be the other, of course, law particularly concerning with the magnitude of an induced electromotive force. In this case, I'm going to use that one, or do that one in terms of an equation, which is going to assist us compare the magnetic flux and the induced motive force. Now, in this case, this law states that the rate of change, which is basically Faraday's law, the rate of change of magnetic flux, which we had given in terms of, so I can just give this one as the rate of change of magnetic flux in terms of a summary, is directly proportional to the magnitude of electromotive force given as such. So this is going to be a summary of the Faraday's law, which states that the rate of change of a magnetic flux is directly proportional to the induced electromagnetic, of course, force given as such. So I can give this one as induced in order to assist us try to interpret this specific law. Therefore, we are going to do a small analysis of that one and try to see what are some of the relationships. So we can give this one in terms of an equation whereby the electromotive force, of course, is equivalent to a negative d phi all over dt. So this is going to give the rate of induced electromotive force, which is directly, of course, which is directly proportional to the magnitude of course, the rate of change of magnetic flux. And from this one, I've introduced this specific aspect of a negative sign. Remember, from Lenz's law, we had mentioned about the concept of opposition of this specific, of course, change causing it. And this is going to imply the opposite direction, of course, which is going to be, of course, a derivative or derived from basically Lenz's law. Now, in this case, we can have a version of this particular equation given as magnitude of induced electromotive force can as well be directly proportional to the, of course, number of turns. So we're going to introduce these specific terms for the number of turns which are included in this particular coils which we have done for our experiment. And therefore, this is going to give us a relationship given as such all over dt. So I've introduced basically a value of n, whereby n implies the number of coils, the number of turns, sorry for that. So basically n implies the number of turns in this particular coil which is going to be under consideration in this particular case. And we're going to see that this particular rate of magnetic flux is going to be, of course, depending on the rate of change. So the faster the change of magnetic flux, the larger the induced electromotive force. Now, from Lenz's law, this was assisted in trying to predict the direction of flow of current using these two notations. And then we have seen that we can as well develop the relationship between the rate of a change of magnetic flux and the induced electromotive force, which is basically going to form a summary of Faraday's law. Now, in our subsequent videos, I'm going to do some of the question sets which are basically going to be depending on these specific laws, and of course, which is going to be emphasizing on the particular case for the concept of a Lenz's law concerning the direction of that specific current. So check our description boxes for various links of other videos, and also subscribe and engage us in the comment section for other discussions in science and mathematics. So that is it for now, guys. Bye. God bless you. Catch us in our next video.